Now just the way we find out components of a vector in a plane, that's a two-dimensional vector which we can represent in general in the xy plane, we can try and find out rectangular components of a three-dimensional vector as well. Though it will be a little more complex, a little more complicated to get the figure correct and to get the expressions, we can easily get it, and we shall see how it simplifies our working with that particular vector as we try to understand the application of components. So, let us first try and look at how a three-dimensional vector looks like in space, and then how do we get its components. Okay. So, let us say we have this the three-dimensional Cartesian coordinate system, the x, the y and the z axis. Z axis here is coming out of the plane of the screen, but we will show it like this. So, understand that this is a three-dimensional picture that I have drawn with x and y axis perpendicular to each other, y and z axis perpendicular to each other, and x and z axis perpendicular to each other, right. So, it is a three-dimensional space with origin O being the corner, being the point of intersection of all the three axes. Starting from the point O, we have a vector A, which is now a 3D vector. It is not lying in the xy plane, it is rather lying in the space, the xyz space. So, how do we understand the presence of vector A in this space, in this particular, on this particular screen that we are using, because the screen is still in 2D, right. So, what we can do is, we can first try to draw the component, or what we can also call as a projection or a shadow of the vector A in the xz plane. Consider the xz plane to be the base plane, where the base of the vector would be. So, it looks something like this. If someone holds a torch or a bulb on the top of vector A over here, then as the rays of the torch will fall on the vector A, they will create a shadow of vector A on the xz plane being the floor plane or the base plane. So, the shadow will look like this vector OP, this line OP will be the shadow. Okay. Now, from this base line OP, the shadow of vector A, we can draw perpendiculars on the x and the z axis to get the components of vector A along the x and z axis. So, how would it look like? From the point P, if we draw a line parallel to the z axis like this, it will cut the x axis somewhere here, and it is this point which we can call as maybe the point Q, and the length OQ then will be the component of vector A along the x axis, because this dotted line that we have drawn will be perpendicular to the x axis. Okay. So, the length OQ will be the x component then. Similarly, from the point P, if we draw a perpendicular onto the z axis, which we can draw like this, this dotted line is actually perpendicular to the z axis, it is in 3D. So, we have to be a little careful while drawing the figures. And then if I call this point as the point S, then the length OS, this length will be the z component of the vector. And in order to draw the y component, what we need to do is, we need to take the tip of the vector A and draw a line which is parallel to the line OP, because it is then that will be a perpendicular to the y axis. So, it will look like this. This will be perpendicular to the y axis, and if we assume that this point is some point T, then the length OT, this length will be the y axis of the vector A. I hope this three-dimensional figure is clear to you. In order to make it more clear, maybe we can consider something like this. We can try and draw a cuboid. Let me draw it separately here. Let us say this is the x axis, the y axis and the z axis, and there is a cuboid that we can try drawing like this. for this cuboid, considering the point O as the origin, then the opposite point, which is the diagonally opposite point to the point O, the body diagonally opposite point, this is the point which corresponds to the tip of the vector A. So, if I join these 2 points, this is our vector A. Okay. I hope you can now compare the 2 figures that I have drawn here. This is our vector A. This point is the same as point Q. This point is the same as point S, and this point is the same as the point T that we have taken in the above figure. So, see that the length OQ is the x-axis, because this line is perpendicular to the x-axis. In fact, we can directly draw a line from the tip of the vector A onto this point Q. This will represent the x component, right, where this dotted line meets the x-axis. Then the perpendicular drawn from the point P to the point S, this is the point P here, and the point S, this gives us the z component, the length OS, and the dotted line drawn from the tip of the point vector A to the point T on the y axis, which will be here, this line will give us the y component, the length OT. Understand that in this above figure that we have drawn, vector A can be taken as the body diagonal of a cube whose side lengths are AX, AY and AZ, right. So, a vector which is in 3 dimensions will have its 3 mutually perpendicular components, each along the x, y and the z axis, representing the 3 sides of a cuboid, which will have its body diagonal as the main vector A. Okay. And not just that, if we know the angles that the vector A makes with the x, y and the z axis, if we know that the vector A makes an angle alpha with the x axis, then we can easily, using what we have done in the in finding out the rectangular components in 2D, in 2-dimensional vector, we can write Ax is equal to A cos alpha. This will require the same trigonometric expressions that we have used previously. Ax will be equal to A cos alpha. If the angle beta is the angle that the y axis makes with the vector A, then we can prove that Ay will be equal to A cos beta. And if the angle that the vector A makes with the z axis is gamma, then Az, the z component of the vector A, can be written as A cos gamma. Okay. And then we can also say that the vector A can be written as the sum of its 3 components, which will be the vector Ax plus vector Ay plus vector Az, where we now know that vector Ax will be nothing but magnitude of vector Ax times I cap, vector Ay will be nothing but magnitude of vector B, magnitude of vector Ay times j cap, and vector Az will be its magnitude times k cap, the unit vectors, right. So, we can simply substitute these values here and get the answers, and we can say that the sum of the 3 components gives us the vector here, the vector A. Also, we can find out the magnitude of vector A by using the same expression that we have used in 2 dimension, but just extending it to the 3rd dimension also. Magnitude will be given by Ax squared plus Ay squared plus Az squared. This expression can actually be proved using geometry. You can use geometry to prove that the length of the body diagonal for this cuboid is given by the squares, the sum of the squares of the 3 sides, the length, the width and the height of the cuboid. This can easily be proved. So, it is from here that you can write this expression as well. So, vector A as well as its magnitude can be obtained in terms of its 3 components, the x, y and the z components, like this. One more thing, from the above expressions that we started with, we can also write cos alpha as Ax by A. See that all we need to do is take Ax on the other side of the expression here. Cos beta can be written as Ay by A, and cos gamma can be written as Az by A, And these three terms that we have written here, cos alpha, cos beta and cos gamma, are together called direction cosines of a given vector. Direction cosines of vector A. What is the relevance of studying direction cosines separately? We can easily prove from the expression Ax is equal to A cos alpha, Ay is equal to A cos beta and Az is equal to A cos gamma, that the magnitude of vector A, which we have written as square root of Ax squared plus Ay squared plus Az squared, which will be square root of A squared cos squared alpha, substituting the values here, A squared cos squared beta plus A squared cos squared gamma. Taking A squared common out of these expressions, we will get A squared within the bracket cos squared alpha plus cos squared beta plus cos squared gamma, and then taking square on both the sides, so that A square gets cancelled out, we will get 1 is equal to cos squared alpha plus cos squared beta plus cos squared gamma here. So, this is how the three angles that a vector makes with the x, y and the z axis are related to each other. The direction cosines are related to each other with this particular expression.